Hi. In this video, we are going to look at the section 2 for our course on Maths Olympiad. And this section will cover quadratic functions. We'll quickly recap some of the theory that is involved, and then we'll look at some problems which will help you approach quadratic equations questions in Olympiads. So let's begin with the basic theory. So if we have a function f of x, which is given by ax square plus bx plus c, such that a is not equal to 0, then this is called a quadratic function. This is called a quadratic function. The degree of the polynomial is 2, therefore it is called a quadratic. And we can write this in the following equivalent forms. We can express this as a into x minus k whole square plus m, where m is some constant. The constant depends on 4ac minus b square. It depends on the coefficients a, b, and c. And this form basically writes it as in form of the vertex. This is called the vertex form because this tells us that the vertex of this parabolic curve will be at x is equal to k. So this is the vertex form. We will see applications of this when we see the graphs of the quadratic function. So if you have something like this, x is equal to k will be the vertex. This is the lowest point of the parabola if it's an upward facing parabola. And if it's a downward facing parabola, it becomes the maximum point, right? So this is one form of writing the quadratic function. Another form is in terms of its roots, which is the factored form. And we write it like this, where x1 and x2 are roots of f of x equal to 0, right? So this form is also very useful sometimes because we might have problems involving the roots. So we can factorize a quadratic polynomial in this form, right? Some of the important properties of the quadratic function that we want to look at quickly here are, first of all, symmetry. So what is symmetrical about the quadratic function? We know that the parabola graph describes a quadratic, and you can see that this line, which is the line x is equal to minus b by 2a, this line divides the parabola into two symmetric halves, right? So there are points here and here which will have the same y coordinate, right? Any point that is equidistant from x by the similar distance will have the same y coordinate if it is equidistant from this vertex point, right? So we can write that mathematically like this: for every real number x, if f of x was ax square plus bx plus c, then for every real number x, we can say f of minus b by 2a plus x will be equal to f of minus b by 2a minus x, right? Also, the discriminant of the quadratic equation or quadratic function can be given by b square minus 4ac, and if discriminant is greater than equal to 0, that implies that f of minus b plus minus root over discriminant by 2a is equal to 0. So basically, these are the two roots. The roots of the quadratic, as you are probably well aware, is this. This expression gives the two roots of the quadratic. The proof of this is elementary. I will not be discussing that. Another thing to keep in mind is that the parabola, the way it opens, the graph of the parabola, it depends on the coefficient of the first term. If a is equal to 0, it's an upward facing parabola. And the graph of the function is such that the function decreases in this region, decreases here, till it hits the vertex, and then it starts increasing, right? Now, if it was a downward facing parabola where a is less than 0, then the graph would increase till the vertex, and then after that it starts decreasing, right? Excuse me. Now, one thing to keep in mind is there are six versions of the parabola graph that you should be aware of. The graphs could be like this. So if you have, this is the graph where it touches the x-axis. This is the x-axis. This is the graph where a is greater than 0 and discriminant is greater than equal to 0. Or actually, we can just say it is greater than 0 because we are saying that there are two distinct roots here. Alpha and beta are the roots. And for discriminant greater than 0, you have two distinct roots. This is the situation where a is greater than 0 because the parabola opens upward, but discriminant is less than 0. So it never cuts the x-axis, so no real roots here. And this is the situation where a is greater than 0, where discriminant is equal to 0. So there are two equal roots. And the x-axis becomes the tangent to the parabolic curve, right? Similarly, you can draw three graphs for the other case also when a is less than 0. Everything is same except a is less than 0. So here you will say discriminant is greater than 0, here discriminant less than 0, here discriminant equal to 0. And in all three cases, a is less than 0. So this is the general nature of the graph of the quadratic. And if you know these basic properties, you can also deduce things like sum of the roots. Sum of the roots is minus b by a, product of the roots is c by a. And you can find out different functions of these roots. Now what we will do is we'll look at some typical problems and learn how to apply these principles in questions, right? So let's begin with our discussion of problems. The first question that we look at is this one. F of x is equal to x square plus ax plus b, and we are given that f of 0 is greater than 1, and f of 4b minus a is equal to f of 3 minus a square. We have to find the minimum value of f of x. The minimum value of f of x. Okay. In all of the problems that we discussed now, you should first make an attempt to solve it yourself. You should pause the video once we write down the problem and then try it yourself. Give yourself sufficient time and then attempt and then see the solution, because that is the way in which you will retain most of the ideas that we discuss. If you just watch the videos completely without trying it yourself, you will not gain as much from the video. So please pay attention to that aspect and try the problems yourself before you see the solutions. So let's go with the solution now. Here we are given this condition. F of 4b minus a is equal to f of 3 minus a square. Now, how can this be true when the function is a quadratic function? There are two possibilities here. There is case 1 and case 2. What is this case 1? Case 1 is if the input to the function are equal. Like if 4b minus a is equal to 3 minus a square, that is your case 1, right? If both the inputs are same, then obviously the parabola will give the same answer, right? So what happens here? Let's analyze this case 1 a little bit. This means 4b is equal to 3 plus a minus a square, or that means b is equal to 1 by 4, 3 plus a minus a square. And if we rewrite this expression a little bit, we can write it like this, 1 by 4, and this we can make the complete square here by subtracting 1 by 4. So we have to add 1 by 4. 3 plus 1 by 4 minus 1 by 4 plus a minus a square. I'm trying to do this only to make a perfect square here, right? So if you see that here, b is equal to 1 by 4, and this is 3 plus 1 by 4, so 13 by 4 minus a minus half whole square, right? This is what is coming. So this tells us that b is equal to 13 by 16 minus 1 by 4, a minus half whole square, right? So what does that mean? Since this quantity is always going to be greater than equal to 0, we can say for sure that b is less than equal to 13 by 16. But is that allowed for us? Let's look at this quadratic again once more. And let's look at f of 0 greater than 1. That is a condition that is given. What is f of 0? F of 0 in the quadratic is actually b, and that is greater than 1. So it can never be then less than equal to 16, right? So this gives us a contradiction. This doesn't satisfy the situation of the problem. So we are going to say that case 1 is eliminated. Case 1 is wrong because case 1 leads to a contradiction, right? So what about case 2? What is another way in which the values of the function could be equal to each other? As we saw that the graph of quadratic functions is symmetric about the vertex, right? So we know that if there are 2 points which are equidistant from x is equal to minus b by 2a for a general quadratic, then the value of the function will be same, right? So we will analyze that situation now. So we have f of 4b minus a is equal to f of 3 minus a square, which means that the 2 points 4b minus a comma f of 4b minus a and 3 minus a square comma f of 3 minus a square are both symmetric, with respect to the vertex of the parabola, with respect to the vertex of the parabola. Correct? So what does this mean? This means that this x coordinate is some distance behind the vertex, and this x coordinate is some distance ahead of the vertex, and those two distances are same, right? So if the vertex of my parabola, the parabola equation was x square plus ax plus b equal to 0, right? This was the equation. And here the vertex would be at x is equal to minus b by 2a, which is minus a by 2, right? So that means that minus a by 2 minus some distance should be equal to 4b minus a, and minus a by 2 plus some distance should be equal to 3 minus a square. I hope you understand the logic here. Because the vertex is at minus a by 2, you have to go some distance behind it and some distance ahead of it for these points to be symmetric with respect to the vertex. So if you add these two expressions, you'll get minus a is equal to 4b minus a plus 3 minus a square, right? So this can get cancelled now, and we end up getting basically 4b minus a square is equal to minus 3. 4b minus a square is equal to minus 3, right? Okay, so now the minimum value of the function, minimum value of f of x. If you think about it, the minimum value of the function happens at the vertex, right? So at the vertex, that will be f of minus a by 2 should be the minimum value of the function. And what is f of minus a by 2? Vertex was at minus a by 2. So f of minus a by 2 is basically a square by 4 minus a square by 2 plus b, which becomes basically minus a square by 4 plus b, which becomes 4b minus a square by 4. And now we already know that 4b minus a square is equal to minus 3. So f of minus a by 2 becomes minus 3 by 4, right? So basically we have found that the value of the parabola at the vertex is equal to minus 3 by 4 just because we realized that there was symmetry in the parabola. And these 2 points were symmetric with respect to the vertex. So notice that we have not used any calculus. The typical ways to approach maximum minima questions is calculus, but in this case, we are using the properties of the parabola that we already understand, right? So hopefully you've got something from the question. The minimum value of the function will be minus 3 by 4. Now we'll move on to the next one. Let's look at the next problem. Question 2. So it says, suppose a, b, c belongs to real numbers and f of x is equal to ax square plus bx plus c, g of x is equal to ax plus b, and it is given that mod of f of x is less than equal to 1 when x belongs to minus 1 to 1. We have to show that first mod of c is less than equal to 1. Second, mod of gx is less than equal to 2 for x belongs to minus 1 to 1. And third, suppose a greater than 0 and maximum value of gx for all x belonging to minus 1 to 1 is 2. We have to find f of x. So this is the problem. We are given a quadratic function. We are also given a linear function. And they have shown us a condition that f of x is mod of f of x is less than equal to 1 whenever x belongs to minus 1 to 1. We have to first prove that mod of c is less than equal to 1. Then we have to show that mod of gx is less than equal to 2 for the same x in the same region. And finally, if it is given to us that a is positive and the maximum value of the linear gx function is 2, we have to find f of x, right? So let's see how we'll go about this problem. The first part of the problem is pretty straightforward. mod of C is less than equal to 1, technically you can see that f of 0 is equal to C, right? So if f of 0 is equal to C, mod of C is basically mod of f of 0, right? That is your mod of f of 0, right? And mod of f of x is always less than equal to 1 when x belongs to -1 to 1. And here x is 0. So x is lying in this range. So therefore, by the condition that is given, mod of f naught f of 0 is less than equal to 1, right? I hope you are understanding. It is very simple because x is 0 here. And when x is between -1 and 1, mod of fx is less than equal to 1. So since we have f of 0 mod is less than equal to 1, follows directly from that condition, right? So the first part is done. There is no issue with the first part. Then let's look at the second part. Okay. Now, in the second part, we have to show that the maximum mod of gx is less than equal to 2, where gx is a linear function. Gx is a linear function, ax plus b. Now, we know that for linear functions, they are always increasing or decreasing because the graph of the gx function will be a straight line. So it will be a increasing straight line if the slope is positive, and it will be a decreasing straight line if the slope is negative, right? So depending on the sign of this a coefficient, we can say that gx will be a linear function either increasing or decreasing, right? So if we have to show that mod of gx is less than equal to 2, then all we need to do for this is to show that at the endpoints of the interval, at the endpoints of the interval -1 to 1, g of 1 mod is less than equal to 2, and also g of -1 mod is less than equal to 2. Why? Because if the two endpoints are less than equal to 2, then any point in between can never be greater than 2, right? Think about it. Think of a graph of a straight line. If at the end point you know that it is less than 2, obviously a point below it can never be greater than 2, right? Similarly, if both the endpoints you have shown that the mod is less than equal to 2, the graph of a straight line can never break and suddenly become greater than 2 somewhere in the middle, right? Because it is a linear and a monotonic function, which always increases and always decreases in any interval, right? So all we have to show in order to prove this for all x in this region is to check the endpoints. So if we check g of 1, g of 1 is simply a plus b, and g of -1 is basically minus a plus b. So we have to show that mod of a plus b is less than equal to 2, and mod of a minus b is less than equal to 2, right? So let's see how we will go about doing that. Let's do that on the next page. So mod of g of 1 is equal to a plus b mod, and we know that that will be equal to, keep in mind your function was ax square plus bx plus c, and in this function we know that f of 0 is c and f of 1 is a plus b plus c, right? So if I have a plus b, I can write that as f of 1 minus f of 0, right? F of 1 minus f of 0 will be a plus b plus c minus c, which is a plus b. And therefore, this we can write as less than equal to mod of f of 1 plus mod of f of 0. This is by triangle inequality. This inequality is true because of triangle inequality. Mod of any two quantities a minus b will be less than equal to the individual sum of the mods, right? So by the property of the function, we have been told that mod of f of x is always less than equal to 1 for x lying between -1 and 1. So this part is less than equal to 1 plus 1, which is 2, right? So we have shown that mod of g of 1 is less than equal to 2, right? Using the properties of the f function, we are able to show that the g function is also bounded, right? Similarly, for g of -1, g of -1 is basically mod of b minus a. And if you want b minus a, the way we can do it is we can say f of -1 is a minus b plus c, and f of 0 is c. So mod of b minus a is equal to mod of a minus b, which is equal to mod of f of -1 minus f of 0. Minus f of 0, right? Mod of f of -1 minus f of 0 will be a minus b plus c minus c, which is a minus b. Again, we follow the same triangle inequality and we say this is less than equal to this, which is equal to 1 plus 1. So we get that mod of g of minus 1 is also less than equal to 2. And because we have checked the two endpoints of the linear function and proved that the modulus at those endpoints is less than equal to 2, we can conclude that the entire graph g of x for x between minus 1 and 1 will always be less than equal to 2, right? So that finishes the proof of the second part of the problem. Now let's move on to the third part. So for the third part, they have said that a is greater than 0 and maximum value of g of x for x belongs to minus 1 to 1 is 2, right? And we are supposed to find f of x, right? Okay. So, fine. So let's think about how we will go about doing this. So g of x maximum value is equal to if a is positive, if a is positive, gx is a linear function, ax plus b. So if a is positive, this is an increasing function, right? Increasing function. So obviously, that means that the maximum value will happen at 1. Maximum value is at x is equal to 1. So gx maximum is equal to g of 1, which is equal to a plus b, which is equal to 2. That is what we have been given in this first sentence, right? And now if you think about it, f of x was ax squared plus bx plus c. So therefore, f of 1 is a plus b plus c. And therefore, a plus b is equal to f of 1 minus c, right? So a plus b is equal to f of 1 minus c. So we have 2 is equal to f of 1 minus c, right? Correct. And we have been given that mod of f of 1 is less than equal to 1, right? Mod of f of 1 is less than equal to 1 and mod of c is less than equal to 1. We have proved this part in the first part of the problem. Mod of c is basically mod of f of 0. So we have these two things, mod of f of 1 is less than equal to 1 and mod of c is less than equal to 1. How is that possible then that f of 1 minus c is equal to 2, right? The only way this will be possible is if this part becomes 1 and this part becomes minus 1. If c is not equal to minus 1 or if f of 1 is not equal to 1, the difference between these two quantities can never be 2. Think about it. If you pause and reflect on it, you will realize that this condition along with these two conditions implies that c is equal to f of 0 is equal to minus 1, right? Great. Also, we have been told that mod of f of x is less than equal to 1 for all x belonging to minus 1 to 1, right? Therefore, mod of f of x is going to be always greater than equal to f of 0, which is equal to c, which is equal to minus 1, right? Mod of f of x is always greater than equal to this c value, right? Which is the f of 0, right? So that means that the c value or the f of 0 value is the lowest possible value of the quadratic function, right? In this interval. So how can it be the lowest possible value of the quadratic function in this interval? That means that the 0 point must be the vertex of the function, right? This implies that f of 0, which is the minimum value of f of x over this interval, f of 0 is the minimum value of f of x in minus 1 to 1. Therefore, x is equal to 0 is the vertex of the graph of the parabola, right? If x is equal to 0 is the vertex, that means in the quadratic, minus b by 2a is equal to 0, which means b is 0, right? It means b is 0. And we already know that if b is 0, A plus B is equal to 2 implies A is 2, right? We are getting A is 2, B is 0. We also got C is minus 1, right? We are using basically all the properties of the quadratic function and the conditions that are given here. So the main point here is to focus on this section. How did we get that C is minus 1? We got it because we knew that f of 1 is less than equal to 1 and mod C is less than equal to 1. And we also got that A plus B is equal to 2, which is f of 1 minus C. F of 1 minus C is equal to 2 implies that C must be minus 1, right? And f of 1 is 1, right? So once we get that, we will realize that if C is minus 1, that means C was equal to f of 0. So 0 is the vertex of the parabola and 0 is the vertex of the parabola. B must be 0. And if B is 0, from A plus B equal to 2, we get A is 2. And therefore, we get the full function actually. The function becomes, I will just write it here. The function becomes 2x square minus 1. F of x therefore becomes ax square plus bx plus c becomes 2x square minus 1. So we are able to find the function because we are able to get the values of a and b and c, right? I hope you have understood this problem. This problem uses the properties of a parabola very intelligently. So hopefully you will learn something from this. Let's look at the next one. Question number 3. So the question says, suppose the graph of y is equal to x square minus k minus 1x minus k minus 1 intersects the x-axis at 2 points A and B, and its vertex is C, The question is asking us to find the minimum possible area of triangle ABC. Find the minimum possible area of triangle ABC. Now, if we draw a rough graph here, we have a parabola like this, and we have vertex C here, and A here, and B here. And we have to find the area of this triangle, right? Area of this triangle, and we have to minimize the area of the triangle, right? Correct. So obviously, area of the triangle will be half base into height if this is h, and this will be the base, right? The base will be the difference between A and B's x coordinates, right? So it will be if A was x1 comma f of x1 and B was x2 comma f of x2, the base will be mod of x1 minus x2, right? And the height will be the y value of the vertex, right? Correct. So if you want to find the vertex point will be minus b by 2a. So minus b by 2a in this parabola will be k minus 1 by 2, comma, minus d by 4a, minus discriminant by 4a. So that becomes minus of k minus 1 whole square plus 4k plus 4 by 4a, which is 4. So this point is given by this expression. So we can simplify it a little bit. It is k minus 1 by 2 and negative of k square plus 2k plus 5 by 4, right? So the height here is easily obtained. Height here is the y value, which is this, right? Okay, now we have to find the distance between A and B, which is mod AB, which is mod of x1 minus x2, and which is equal to root over x1 minus plus x2 whole square minus 4x1 x2, right? Where x1 x2 are the roots, so this is going to be sum of the roots whole square minus 4 times the product of the root. This is a standard step in usual quadratic equation questions, and if you calculate this out, it will come out to be root over k minus 1 whole square plus 4 times k plus 1, which is equal to root over k square plus 2k plus 5. So this is basically the base of the triangle. So area of the triangle ABC, S of ABC will become half base into height. So half into this into height is mod of this. So it becomes 1 by 8 k square plus 2k plus 5 to the power 3 by 2. Now we have to find the minimum value of this. So we can get that by expressing this as a perfect square. It is k plus 1 whole square plus 4 whole to the power 3 by 2, right? And this quantity inside is always greater than equal to 4. Therefore, the area S is greater than equal to 1 by 8, 4 power 3 by 2. Why is it greater than equal to 4? Because we have a perfect square here, which is always greater than equal to 0. So this is becoming basically 1, right? So area is greater than equal to 1 is coming after you evaluate it. So basically what we have found out is the minimum possible area of the triangle. All we did was looked at the graph, found the vertex and found the difference between the two loops, right? So hopefully that is a pretty easy one for you. Another question that we look at now is like this. So let f of x be equal to ax square plus bx plus c, where a is greater than 0. And let x1 and x2 let x1 and x2 be the roots of f of x, be the roots of f of x equal to x with the properties x1 is greater than 0 and x2 minus x1 is greater than 1 by a. Okay. Now, the question is saying, suppose 0 is less than t is less than x1, find which is bigger. Which is bigger? Is it f of t or x1? The question is slightly unusual. You are supposed to find out which number is bigger, f of t or x1, given all of this information. F of x is a quadratic, it's an upward facing quadratic because a is greater than 0. x1 and x2 are roots of the equation f of x is equal to x. And the properties of the roots are such that x1 is positive and x2 minus x1 is greater than 1 by a. Also, t is some number between 0 and x1, right? Okay, so let's start by looking at the equation. Ax square plus bx plus c is equal to x was my equation. So the equation can be rewritten like this: ax square plus b minus 1x plus c equal to 0. And here, we know that the roots of this equation are x1 and x2. So we can say x1 plus x2 is equal to minus of b minus 1 by a. So 1 minus b by a. And x1, x2 is equal to c by a, right? Okay. Also, we know that x1 satisfies this equation. So a x1 square plus b x1 plus c is equal to x1, right? That is true. We have these conditions so far. This condition here and another condition here and this condition, right? Now, in order to decide which one is bigger, most of the times we can try and find out what is f of t minus x1, right? If this turns out to be positive, then f of t is bigger. If it is negative, f of t is smaller, right? So let's evaluate that. That becomes at square plus bt plus c minus x1. And because ax1 square plus bx1 plus c is equal to x1, we can replace this x1 with this expression, right? So we can write at square plus bt plus c minus ax1 square minus bx1 minus c, which becomes basically a t square minus x1 square plus b t minus x1. If we take the factor out, we will say that t minus x1 common, and we have a into t plus x1 plus b. And if we even take an a outside from here, because a is also positive, a outside, a into t minus x1, this becomes t plus x1 plus b by a, right? Great. So f of t minus x1 is coming out to be this expression. Here we know the sign of a is positive. We know t minus x1. T minus x1 is negative because x1 is bigger than t. So this is negative, this is positive. We have to figure out the sign of this term, right? T plus x1 plus b by a, right? Now, from this expression, we can say that x1 plus b by a is equal to 1 by a minus x2, right? 1 by a minus x2, correct? This is following directly from this expression, correct? So x1 plus b by a is 1 by a minus x2. So therefore, t plus x1 plus b by a, which is the term that we need to figure out here. T plus x1 plus b by a is basically t plus 1 by a minus x2, right? T plus 1 by a minus x2. And now, because t is less than x1, we can say that this is less than x1 plus 1 by a minus x2, right? I hope everybody is understanding what I'm doing here. Because t plus 1 by a minus x2 is equal to this and t is less than x1, I have written this is less than this. And now we know that we have x2 minus x1 is greater than 1 by a. So this term is actually 1 by a minus x2 minus x1, right? 1 by a minus x2 minus x1. So, but x2 minus x1 is greater than 1 by a. So that means this term is negative, right? And the required term is smaller than this, and this itself is negative. So therefore, this term is also negative. This comes out to be negative. So overall, we are getting f of t minus x1 is coming out to be positive. Positive overall, right? If f of t minus x1 is positive, that means that f of t is greater than x1. So notice how we have used the different properties of quadratics. We have used this condition. We have written this f of t minus x1 like this. Then we factorized it. We used the sum of the root stuff. We used this equation. And basically use the conditions of the problem to figure out what should be the case here, right? So hopefully you've understood something from this problem as well. Let's go on to the next one. Question number 5. This is from the 2017 China maths competition. So you should like this question. It says, suppose A and M are real numbers, such that the inequality mod of x square minus kx minus m is less than equal to 1 holds for all x belong to A to B. Okay, we have to show that B minus A is less than 2 root 2. So basically K and M are real numbers such that the quadratic has a modulus less than equal to 1 for all x belonging to A to B. Right. So all x belonging to A to B, the modulus of the quadratic is less than 1. Ideally, that means that you can say that mod of f of A is less than equal to 1. You can say mod of f of B is less than equal to 1. You can even say mod of f of A plus B by 2 is less than equal to 1. Because all of these numbers are lying in the interval A to B, right? So typically when you have problems like this, you should try to take different cases and get different inequalities. Because this inequality is satisfied for all values between A to B, you can take 3 separate cases, right? So if I take this case from here, what we can say is that A square minus KA minus M will be less than equal to 1, right? And from here we can say B square minus KB minus M will be less than equal to 1. And from here we can say A plus B by 2 whole square minus K times A plus B by 2 minus 2 minus M will also be less than equal to 1. But you can say that in a different way as well. We can say that it is greater than equal to minus 1 also, right? If the modulus is less than equal to 1, we can write it as between minus 1 to 1. So we can write it as greater than equal to minus 1 also. We will see the benefit of that soon. So what I will do is first I will add these two inequalities, right? If I add these two inequalities, I get a square plus b square minus k a plus b minus 2m is less than equal to 2, right? Great. And if I double this inequality, what will happen? I will get basically a plus b whole square by 2 minus k times a plus b minus 2m is greater than equal to minus 2, right? And if I multiply it with minus 1, I will get a plus b by 2 whole square by 2 plus negative of this plus k times a plus b plus 2m is less than equal to 2, right? See, what I have done here is basically multiplied this inequality by 2 and then multiplied it by minus 1. Why am I doing all this? Because I want to eliminate this term and this term. I want to get a b minus a stuff, no? Because I have to show an inequality on b minus a. And I have a square plus b square here and minus this stuff here. If I now add the two inequalities here, this will cancel this will cancel this, and I will have a square plus b square minus this stuff is less than equal to 4, right? So let's see what happens. A square plus b square minus a plus b whole square by 2 is less than equal to 4 comes on adding the two inequalities on the previous screen, right? So you'll get twice of a square plus b square minus a square plus b square plus 2ab by 2 is less than equal to 4. And this simply becomes a minus b whole square. If you simplify this, this will become a minus b whole square by 2 is less than equal to 4, which implies a minus b whole square is less than equal to 8, which implies that mod of a minus b is less than equal to 2 root 2, right? Mod of a minus b is less than equal to 2 root 2 is what we need to prove. We have shown that means b minus a will be less than equal to 2 root 2 and between minus 2 root 2 and, right? So the question is solved by taking three conditions for f of a less than equal to 1, f of d less than equal to 1, and f of a plus b by 2 is greater than equal to minus 1. These are all following from the condition of the problem. And then we added these two and subtracted with double of this. That's what ultimately we are doing, and we are able to quickly prove it, right? Let's look at another problem. This is a Russian Maths Olympiad question. It's a short question. You either get it or you don't get it. So let's read the problem first. Suppose A, B, C are three different positive integers, three different positive integers. Determine whether there exists a quadratic function f of x with integer coefficients such that its leading coefficient is positive. And there exist integers x1, x2, x3 satisfying f of x1 is equal to a3 I think it is not f of x1. There exist integers a, b, and c such that f of a is a3, f of b is b3, b cube, and f of c is c cube. We have to basically find out if there is a possible quadratic with integer coefficients such that its leading coefficient is positive and there exists integers such that f of a is a cube, f of b is b cube, and f of c is c cube, right? So this is a question where you just have to sort of guess the function. So we have some information, we need to make a quadratic, first of all. F of x is a quadratic. And we need to somehow get f of a is equal to a cube for an integer a, f of b is equal to b cube, and f of c is equal to c cube. So it's a question where you just have to guess possible answers, right? So think about it. You can start thinking by f of x is x cube, but first of all, that will satisfy these three conditions, but it is not a quadratic, right? You need to make it a quadratic as well, right? So you need to make it a quadratic in such a way that f of a is still a cube and f of b is still b cube, right? So how can I do that? We need to subtract x cube from it somehow, right? So if I subtract a product of x minus a, x minus b, x minus c, right? Think about this. When you subtract from x cube these things, basically the x cube term gets cancelled, right? This will start and become basically x cube minus x cube plus, it will become a plus b plus c x square minus ab plus bc plus ca x plus abc. If you evaluate this expression, this is what it becomes. An x cube got cancelled, and this is ending up as a quadratic, right? This ends up as a quadratic. So basically, this is a good guess because it still satisfies the conditions of the problem, right? It still satisfies the fact that f of a is equal to a cube, because if you put a, these terms vanish, a, b, and c, these terms vanish, and you are now have a quadratic. A plus b plus c is positive, the leading coefficient is also positive, and you are satisfying the conditions of the problem. So the answer actually becomes basically f of x is equal to a plus b plus c x square minus ab plus bc plus ca x plus abc. But the way you get it is f of x is equal to x cube minus x minus a, x minus b, x minus c. Because that is how intuitively you start thinking of the quadratic, right? So this is a trick question. It's not like you can get a lot of theory out of it. You just realize that sometimes you need to guess functions. Let's move on. Let's look at the next one. Question number 7. Suppose f of x is given by x square plus a square plus b square minus 1 x plus a square plus 2ab minus b square, right? And this is an even function. F of x is an even function. You have to find the maximum possible value, possible value of the minimum value of f of x. So there will be some minimum value of f of x. We have to find the maximum possible minimum. So interesting question. The only thing that has been given to us is that f of x is even. Now, if you understand that if it's an even function, f of minus x must be equal to f of x, right? That is the definition of an even function. And if you think about it, you cannot have an even function with a odd power of x. This cannot be possible, right? This term, if this term is present, the function cannot be even. You can have only even powers of x or have constant terms. So just the fact that the function is even implies that coefficient of x term is 0, which implies that a square plus b square is equal to 1, right? Just because the function is even, we know that a square plus b square is equal to 1. And now the minimum value of f of x is supposed to be found, right? Minimum value of f of x, which now looks like x square plus a square plus 2ab minus b square, right? So it is obvious that this x square is always greater than equal to 0. So this is always greater than equal to a square plus 2ab minus b square, right? So the minimum value of f of x is this. So we have to maximize the value of the minima. So maximize the value of a square plus 2ab minus b square, given the condition, given that a square plus b square is 1, right? This condition has to hold, and in that situation, we have to find the maximum possible value of this, right? Now, because of a square plus b square is equal to 1, that gives us a hint that we can parameterize a and b and use a little bit of trigonometry instead. We can say a can be cos theta and b can be sin theta, right? If a square plus b square is 1, there must be some theta for which this is true, right? So if you do that, you will get basically cos square theta plus 2 cos theta sin theta minus sin square theta is the value of this expression. And this is basically cos 2 theta plus sin 2 theta. Using the trigonometric identities for double angles, you can say cos 2 theta plus sin 2 theta is equal to this, which is again less than equal to root 2. Why is this less than equal to root 2? Because we have some standard theory of trigonometry. If a cos theta plus b sin theta is my function, then that will always lie between minus of a square plus b square root 2 plus root over a square plus b square. Here, a and b are 1 and 1. 1 cos 2 theta plus 1 sin 2 theta, it will always be less than equal to root 2, right? So root 2 is the maximum value of this function under the condition a square plus b square is equal to 1. So basically our answer for the question, the maximum possible value of the minimum value of the function is equal to root 2. So I hope you understood what we are doing here. It's a pretty interesting question and pretty simple as well. Let's move on. The next one that we look at is basically this one. Question 8. Let A and B be real constants. Real constants. Suppose for all real numbers A, the graph of y is equal to k square plus k plus 1 x square minus twice of a plus k whole square x plus k square plus 3ak plus b always passes through a, which is 1 comma 0. We have to find the values of small a and small b. And second, if b is the other intersection point of the graph the graph of the function and the x-axis. And the x-axis. Find the maximum value of mod of AB as k varies. So let's try to understand this problem. A and B are real constants. And the question is saying, suppose for all real numbers k, the graph of this function always passes through a 1, 0. So if you notice that this is passing through the x-axis, 1, 0 is on the x-axis. So a 1, 0 implies that x is equal to 1 is a root of the quadratic of f of x, right? X is equal to 1 is a root of f of x. So if you just put x is equal to 1 in that, what will happen? We'll say k square plus k plus 1 minus 2 times a plus k whole square plus k square plus 3ak plus b equal to 0. This must always be true for all real numbers k, right? So if you simplify this a little bit, you will realize that k square and minus 2k square will get cancelled. And you will get an expression just as linear in k, 1 minus a k plus b plus 1 minus 2a square equal to 0, right? Now this expression is valid for all real k. This expression has to be true for all possible values of k, which cannot happen if this term exists. If this term is present, then it keeps changing. So how can these constants be always equal to that, right? So that implies that the coefficient 1 minus a here must be 0. 1 minus a is 0 because this equation has to be true for all real k. That is going to happen only if 1 minus a is 0 and b plus 1 minus 2a square is also 0, right? So basically that gives us a is equal to 1, and if a is equal to 1, then b is also equal to 1, right? A is equal to 1 and b is equal to 1 follow just from the fact that x is equal to 1 is a root of f of x for all real k. I hope you are understanding what is happening here. So if a is equal to 1 and b is equal to 1, the quadratic now looks very different. The quadratic, we are saying that b is the other intersection point of the graph of the function and the x-axis. So b is the other root of the quadratic, right? So we'll write it on the next page. The equation is like this: k square plus k plus 1 x square minus 2 1 plus k whole square x plus k square plus 3k plus 1 equal to 0. This is the equation. 1 is a root and b is a root. So if b point is given by x2 comma 0, we have basically 1 and x2 are roots, right? If 1 and x2 are roots, we can say product of the roots is 1 into x2 is equal to c by a. So k square plus 3k plus 1 by k square plus k plus 1, right? That is the product of the roots. So x2 must be this, right? Great. So if I simplify this expression, I get k square plus k plus 1 x2 is equal to k square plus 3k plus 1. So I can rewrite this now as 1 minus x2 into k square plus 3 minus x2 into k plus 1 minus x2 equal to 0, right? This equation is coming, and this is true for all real k. Therefore, the discriminant of this quadratic must be positive. This equation must be holding for all real k because the question has mentioned that. So discriminant must be positive. So we get 3 minus x2 whole square minus 4 1 minus x2 whole square is greater than or equal to 0, which implies that 3x2 square minus 2x2 minus 5 is less than or equal to 0 after simplifying a little bit. And that gives us the fact that if this quadratic is less than equal to 0, then x2 must lie between the roots of this quadratic. So -1 is less than equal to x2 is less than equal to 5 by 3. If you find the roots of this quadratic, you will realize that they are -1 and 5 by 3. And that means -2 is less than equal to x2 minus 1 is less than equal to 2 by 3. So mod of x2 minus 1 is always less than equal to 2. X2 minus 1, when you take a mod, you will get always less than equal to 2, right? And why are we taking mod of x2 minus 1? Because that is equal to the mod of AB, right? Because A was 1, right? We have to find the mod of AB and the maximum value of the mod of AB. The maximum value of mod of AB is basically 2. I hope you are understanding what we are doing. We said that we already know 1 is a root, so x2 is the other root. We took product of the roots. We got a quadratic in terms of k. And since this equation has to be satisfied for all real values of k, we can say that the discriminant must be positive for this quadratic in k, right? Because k has to be real, right? So from there, we get a condition on x2. And once we get a condition on x2, by simplifying, we can say that x2 must lie between the two roots. And therefore, the distance AB we can find by finding out the value of mod of x2 minus 1. Okay. So we have discussed quite a few problems right now. We will make one follow-up video for this topic where we'll discuss some more tricky types of problems. And then we'll conclude this section of the course, which is about quadratic functions. I hope you have learned something from this video, and stay tuned for the next one. And hopefully you can take as much out of it from the course. See you in the next one.